900 years ago, two worlds were at war. The Christian and Islamic empires, who for centuries had almost no contact, now brutally clashed in this Christian crusade to control the Holy Land. And while soldiers on both sides fought and bled, European scholars thought and read, and realized they were standing in the face of an unprecedented opportunity, not to defeat their Muslim counterparts, but to learn from them. See, at this time, the Muslim world was far more advanced than Europe in almost every way. And now with Muslim libraries plundered and lands occupied, European scholars had access to this knowledge for the very first time, and they were not letting it go to waste. A disorganized flurry of intellectuals ensued on these previously Muslim lands to gather and eventually translate everything they could find. And one of the most successful among them was an English scholar by the name of Adelard of Bath, who discovered a 13-book, 500-page mathematical encyclopedia, the first 6 books of which is an absolute compendium of geometric knowledge unlike anything the Europeans had ever seen. Each page after page of these books contains a geometric fact, written in Arabic, remember, followed by a diagram and an in-depth proof demonstrating exactly why this fact has to be true. Suffice to say, this book was leaps and bounds beyond anything the Europeans were doing. And after Adelard's translation was published, it spread like the plague. I mean, just imagine if right now we found a math textbook that was generations or centuries ahead of anything we were doing. The consequences would be enormous. After Adelard, more and more translations of this work were made, and for the next 700 years, this was used as the foundational math textbook every learned person in the West should know. Not because of its historical significance, but because it was still the most comprehensive and relevant geometry book ever devised. Literally to this day, this math encyclopedia has been printed in the second most editions and languages only behind the Bible. And the wild thing is, at the time of Adelard's discovery, it was not new to Europe at all, but actually very, very old. What Adelard had unearthed was not an original Muslim work, but was an Arabic translation of Euclid's Elements, the magnum opus of ancient Greek mathematics, written well over 1,000 years before Adelard and some 800 years before Islam. The Elements, as it's called, was once very popular all over the ancient Greek and Roman world, but almost every copy was lost during the Dark Ages. It only survived preserved in Arabic translations, continuously copied and also built upon, by the way, in the Muslim world. And the origin of it all is this guy right here, Euclid of Alexandria. Yes, the Library of Alexandria, who you can see from his depiction here, is always pictured with the same two tools, a straight edge and a compass. And the reason Euclid is consistently associated with these two tools is because Greek geometry, and so by extension the geometry rediscovered by Adelard that became the standard in the West, was obsessed with trying to do all of geometry with just these two tools. Just a straight edge and a compass. You watching this video right now might be taking a geometry class where doing things with a straight edge and compass, whether you like it or not, is going to be a big part of it. And the reason is because even though we don't use Euclid's Elements directly as a textbook anymore, we still often teach geometry in the way the Greeks approached it. And my question, which is the question that every geometry student should ask, is why? Why were the Greeks so obsessed with using just these two tools, just the straight edge and compass when doing geometry? And what about their approach was so revolutionary that it had such a big impact that it changed the course of Western thinking and mathematics forever? That's what we're going to find out. To truly understand where the straight edge and compass come from, we have to go back to the origin of Greek geometry itself, ancient Egypt. You see, according to the ancient Greek historian Herodotus, who was the very first historian in the West, by the way, no big deal, the story of geometry begins with the Egyptian pharaoh Ramses II. Now, Ramses was kicking in the 1200s BC, and when I say kicking, I really mean more stabbing and conquering, because Ramses famously went around subduing every nation to which he came, and was almost burned alive by his brother. But when he settled down, Ramses had one thing on his mind: land distribution. See, still according to Herodotus, Ramses decided to give every Egyptian a parcel of land. and he would generate income by taxing them based on how much land they had. Now, this was complicated by the fact that the Nile would flood every year, and so it could potentially destroy someone's land, or at the very least destroy the markers separating one person's land from another. So every flood, the government would have to send workers by to resurvey the land. And it's from these government land surveyors, Herodotus claims the Greeks learned the art of
Geometria.
geometry. Confused? Good, that means you're paying attention. I was confused at first too, until I saw the breakdown of the word geometry. Geometry literally is geo, so earth, metry, measuring. It literally means earth measuring, or what we'd probably call today land surveying, which might at first feel very different than what we think of when we think geometry, but really consider it. What is land surveying all about? It's about measuring/creating distances and angles on the land, right? Which requires a lot of geometric knowledge to pull off. The land surveyors just only think about this knowledge in the context of land measuring. But you can imagine how a general understanding of geometry could potentially evolve from generalizing these land surveying concepts, literally from the ground up. Now, important disclaimer here, this story you just heard about the origins of geometry is just that, a story. One Herodotus heard about a time hundreds of years before his own birth and relayed to us, meaning we could be significantly off in the details and the timeline and everything here. But every Greek writer, whether getting their information from Herodotus or another source, all agree their geometry originated with these ancient Egyptian land surveyors. So who am I to say any different? Especially because these ancient surveyors definitely did exist, and they were awesome. They were called the Harpodonopti, which literally means rope stretchers. And you can see them pictured here in this ancient carving complete with their coils of rope. Now, they were called the rope stretchers because they did land surveying with stretched ropes. The idea is if you pull a rope taut, it makes more or less a perfectly straight line. And then if you tie knots at regular intervals along this rope, you've essentially made a giant ruler. One that you can use to measure out the boundary of an existing plot of land or create the boundary of a new plot of land. Now, the actual Egyptians measured distance in cubits. That's just the length from the elbow to the tip of the middle finger here. And it's thought that each of these coils they carried was 100 cubits long, aka 1.5 football fields. So you can imagine, especially if they had a few of these coils, they could measure out large plots of land. To test if this would actually work though, let's do a toy example. Say you wanted to lay out a square plot of land that was 12 cubits by 12 cubits. I think the most obvious thing to do would be to take your rope and measure out 12 cubits for your first side, and then measure out 12 more cubits from there for your second side, and 12 more cubits from there to be your third side. But now we have a huge issue. If you measure the distance from this last corner we just stopped at to our starting corner, it's going to be way more than 12 cubits. This is because while we did our best to eyeball it, at each corner we did not make a perfect right angle, meaning the shape we end up with is significantly off from being the square we wanted. And this is a big issue because we know from records that the ancient Egyptians liked to use square or at least rectangular plots of land whenever they could. Likely because they make areas easier to calculate, taxes easier to assess, and they just make everything easier to organize. So they must have been able to lay out rectangles somehow. But how? I mean, seriously put yourself in their shoes for a second. If you were an ancient Egyptian land surveyor, how would you do it? How could you use just the ropes you have to lay out a square/rectangle in a way that guarantees you get right angles every single time? Well, there are a few ideas for this, but the most common is that they use what's called the 3-4-5 method. Here's how that works. Now, you've probably heard of the Pythagorean theorem, right? That's just the one that says in any right triangle, one side squared plus the other side squared has to equal the third side squared. But what people don't tell you is that this theorem also works backwards. Not only will every right triangle work in this way, but any triangle where one side squared plus another side squared equals the third side squared must be a right triangle. A classic example of this is a 3-4-5 triangle. Since 3 squared plus 4 squared equals 25, which does in fact equal 5 squared, This means any triangle with side lengths 3, 4, and 5 must be a right triangle. Now, did the Egyptians know any of this theory? Probably not, but it is conceivable to think they could have figured this out, at least in the 3, 4, 5 case, just by experimenting with some ropes. Once you know this though, the clever idea is, if you want to make a right angle, all you have to do is construct a 3, 4, 5 triangle. Because if you do that, then the angle opposite the 5 has to be a perfect 90 degrees automatically. So if you start with the first 12 cubit side, you can make a right angle on the left end like this. First, measure out 3 cubits from the left end and put a stake there. Then secure a 4 cubit rope to the corner and a 5 cubit rope to that new stake and pull them both taut together. Now what we've created is a 3, 4, 5 triangle. So this has to be a right triangle. Then you can extend a 12 cubit rope in the same direction as that 90 degrees to make the second side of your square. From there, you can just do that whole process again. Use the 3, 4, 5 method to make a 90 degree angle and extend another 12 cubit rope in that direction to make the third side. Now finally, just connect the 2 loose ends here and you've made a perfect square. Now to be clear, we've not found any actual artifacts from the Egyptians documenting their rope stretching methods, so it's impossible to know if they actually did exactly this. But the 3, 4, 5 method would have worked, and given the simple tools they had, it seems they would have had to have done something tricky like this. But do you see the genius of this? The Egyptians did something which on the surface feels impossible. They used ropes to create an angle. Ropes don't do angles. All ropes do directly is measure distance. But if you're very clever, you can use these ropes in just the right way to make a perfect right angle. If you're smart, you don't need advanced tools to do complicated things. The Egyptians proved you can use simple tools, but in a very clever way, to do complicated things. And it makes you wonder what other seemingly impossible things could you accomplish with just simple tools if you were only smart enough. And that's exactly what the Greeks would wonder when their first mathematician went to Egypt and came back with some bold new ideas. We're now going to shift our focus away from the floodplains of Egypt clear over the Mediterranean Sea to the Greek world. Or the time of Ramses II and the rope stretchers, there is not much math happening at all. You see, even though the Greeks would eventually become famous for creating the foundation of Western philosophy, astronomy, and mathematics, at this time they were doing none of that. And in fact, for the next 500 years, they would remain seemingly oblivious to these topics until finally they were taught the basics by the Egyptians. And by they, I really mean he. Because according to the sources, there is one man who was originally responsible for bringing philosophy, astronomy, and mathematics to the Greeks. And his name was Thales of Miletus. You see, before this time, the Greeks and the Egyptians had very little contact with each other. It wasn't until the Egyptians started hiring Greek mercenaries the two even entered the texting phase. But that was the start to a working relationship. And shortly after this, the Greek city-state Miletus started the first Greek trading post in Egypt. And it was around this very time, in this very city-state of Miletus, that Thales was born. And because he was Milesian, it seems he was able to leverage this new relationship between Miletus and Egypt to be the first Greek allowed to study with the Egyptian priests, who were like the all-star scientist, mathematician, academics of the day. From the priests, he presumably learned all the genius techniques of the rope stretchers, but also all the other very practical mathematical knowledge the Egyptians had about creating formulas to calculate areas and volumes, which they had for some increasingly complicated shapes. We actually made a whole video about that here. If you're interested, it gets wild. With this studying done, however, Thales returned to Miletus, where he exposed the Greek world to these Egyptian-inspired ideas for the first time, becoming Greece's first philosopher, astronomer, and mathematician. Yes, all three of these topics have their roots in one person. I mean, there may have been some dudes before Thales that looked at the sky and thought stuff, but he was the guy that started the Greek school of thought in all these topics, and advanced them substantially while he was at it. And in my circles, he's most known for making groundbreaking discovery after discovery in geometry, but not the geometry you might think. Interestingly enough, Thales did not seem to practice the geometry of areas and volumes we find standard in Egyptian math documents. Instead, he pioneered a new kind of geometry, one focused on the relationships between lines and angles and distances, one seemingly not inspired by Egyptian mathematics, but by Egyptian land surveying. For example, you may have heard that when two lines intersect like this, these two angles opposite each other have to be equal. That was Thales. He was the guy that figured that out. Or maybe you've heard that in an isosceles triangle, so a triangle where two of the sides are equal, these two angles at the base have to be equal as well. That's also Thales. He was that guy too. And notice there are no formulas, areas, or volumes to speak of here. Every theorem is just about certain lines, angles, and distances and how they're related. And I say this is likely inspired by the Egyptian rope stretchers, because if you think about it, understanding how lines, distances, and angles are related is kinda exactly what they did. I mean, for one, because they only worked with ropes and pegs, the only figures they could even make and care about are ones that involve just lines, distances, and angles, exactly what Thales was studying. And what's more is that any land surveying technique they could have invented would have required them to have some understanding of how distances and angles are related. For example, if they did use the 3-4-5 method, they would have to know that the side lengths of a triangle and the angles in a triangle are related. In particular, the side lengths are 3, 4, and 5 only if this angle is a right angle. Once they know this, inventing the 3-4-5 method for constructing right angles would be easy. As genius as this is, however, the Egyptians only really seemed to know this one relationship, and they only used it for this one right angle trick. What Thales did is explore what other relationships might be out there, and what other genius tricks could they beget. Over the course of his life, Thales collected more and more of these relationships, effectively expanding the theory of how lines, angles, and distances are related from just this one fact to a whole organized study. A study the math historian George Ullman dubbed the geometry of lines. And just like how the rope stretchers used the relationship they found to invent the right angle trick, Thales was able to leverage the relationships he found in very clever ways to do seemingly impossible things with very simple information. Almost certainly the most epic example of this is when Thales used just his mind and some shadows to measure the height of the Great Pyramid of Giza. And the idea behind this one is genius. What Thales noticed is that when the sun gets real low, an object's shadow gets real long, longer than the object is tall. And when the sun gets real high, like overhead, the length of an object's shadow gets really short, shorter than the object is tall. But at some very special time each day, there's a transition point, when the length of an object's shadow exactly equals its height. And importantly, this very special time of day is the same for all objects. So at the exact time when a stick's shadow length equals its height, Thales' shadow length will equal his height, and most importantly, the Great Pyramid's shadow length will equal its height. The height of the Great Pyramid and its shadow length are related. So all Thales had to do is wait for the time of day when his staff's shadow length exactly equaled its height. And then at that precise moment, measure the length of the Great Pyramid's shadow. Because he waited for the time when shadow lengths are equal to heights, whatever number he gets for the length of the shadow will be the height of the Great Pyramid.
So, for example, the closest thing I could find to a Great Pyramid in America is the Washington Monument. But just like the Great Pyramid, this was the tallest structure in the world when it was built. I'm going to find out exactly how tall it is just using a couple of sticks and my feet. Sounds like a tall task. Using Thales' idea, all we have to do is wait for the time of day when my stick's shadow has the same length as its height. At that exact time, the Washington Monument shadow will also have the same length as its height. So if I just measure the length of the Washington Monument shadow, I'll get its height for free.
There we are. That is 1, 2, 3, 4. 116. 116, and what do you want to call that? 10.5 inches? Yeah. Okay, so we're 116. Remember 10.5 inches. 534, 535, 536, 4 inches.
Okay, so we measured it's 537 feet and 2.5 inches from the tip of the shadow to the outside of the monument here. Now, technically, we need the distance from the tip of the shadow to the center of the monument. And unfortunately, the electromagnetic forces on my atoms are preventing my body from getting to the center of this monument. However, we did measure, and the base of the monument is 55 feet. So let's just say it's half of that from the outside to the center of the monument. So that's 27.5 feet. And so we're measuring the distance from the tip of the shadow to the center of the monument to be 537 feet and 2.5 inches plus 27.5 feet, which is going to be 564 feet and 8.5 inches. And because the length of the shadow equals the height of the monument, that means the height of the Washington Monument should be 564 feet and 8.5 inches. Is that right?
Okay, according to Google, height of the Washington Monument. According to Google, the height of the Washington Monument is 555 feet and 5 1/8 inches tall. Meaning we're less than 10 feet. Just using the shadows from the sun and my foot feet and a stick in the ground, we've got within less than 10 feet of the answer. That's not bad. I'm very happy with that. I'm very okay with that. That's a success.
And once again, how clever is this? Just by realizing that shadow lengths and heights are related, Thales was able to get the impossible to measure height of the pyramid just by using the simple to measure shadow. So in several ways, Thales' geometry of lines is truly a direct outgrowth of land surveying techniques, which is why it's no accident Thales' geometry focused so much on lines, circles, and right angles, because those were the figures that lined up with the land surveying instruments of the day. The rope, which when pulled taut makes a physical line. The rope and stake, which when the rope is pulled taut and walked around the stake makes a physical circle. And a right angle tool, of which there are a few the Greeks could have had access to, but all could be used to make physical right angles. And so every one of Thales' theorems, while today are seen as abstract geometric truths, back then may have been viewed as practical land surveying techniques, detailing how line tools, circle tools, and right angle tools can interact to create complicated shapes, just like the 3-4-5 method. The Greeks also had many versions of all these tools they could use to construct shapes on a smaller scale, like for masonry, carpentry, or drafting. They were the straight edge for lines, the compass for circles, and the carpenter's square for right angles. And Thales' theorems are equally applicable in understanding how these tools can interact to do complicated things as well. A great example of this is a little trick you can do with Thales' most famous theorem that today we call Thales' theorem. It asserts that any triangle you build off a diameter line of a circle, where all 3 points are on the boundary, will be a right triangle. No matter where this corner is opposite the diameter, if it's on the circle, its angle will be a 90-degree angle. Interesting, right? And again, notice this is pointing out a relationship between two parts of a geometric object, In this case, the relationship being that this line is a diameter line if and only if this angle is a right angle. But once we understand this, it will allow us to use just a simple right angle tool to do something that plagues at least this modern man to this day. Find the exact center of a circle. Here's the problem. Imagine you're trying to make a spinner wheel to decide what to do today. So you trace out a perfect circle using a bucket on some foam board, and then you go to poke a hole in the exact center to put the axle. But immediately you have a big problem. Where's the center of this circle? If you just guess, you could be close enough, but if you're off, your spinner just won't spin right. So it'd be really great if there's a more scientific way to find the center of this circle. And luckily there is, using Thales' theorem. And the idea is very simple. We know that any diameter line of a circle must go through its exact center. And so if we had two different diameter lines of a circle, the point at which they meet has to be the center. Now on the surface, this isn't very helpful because it's hard to draw a diameter line when you don't know where the center of the circle is. But here's where Thales' theorem comes in. Thales' theorem says that if you draw a triangle in a circle, and this angle here is a right angle, this side has to be a diameter line. So using just our right angle tool, we could draw a right triangle on our circle, and since this angle is a right angle, this line has to be a diameter. We could do this whole process again to make another right triangle and therefore get another diameter line. And then as these are both diameters, the point at which they intersect must be the exact center of the circle. Meaning we can make a perfectly balanced spinner, and then I can use it to decide what to do with the rest of my day. So once again, this is genius. Right angle tools were not built to find the center of circles, they just make right angles. But using Thales' theorem, we can use this simple right angle tool in a clever way to do something more complicated. The ancient Egyptian surveyors would be proud. And even though Greek geometry will advance and evolve over the years, it will always continue down the same line of inquiry the rope stretcher started so many years before. How are lines, distances, and angles related? And how can we use those relationships to do impossible things? After Thales brought the geometry of lines back from Egypt, it would eventually go on to ignite the imagination of intellectuals all over the Greek world. Even though Thales only uncovered a handful of theorems, even the existence of these theorems raised a bunch of interesting questions. Mainly, if these exist, what other theorems are out there? In what other fascinating ways are lines, distances, and angles related? As a growing number of mathematicians worked on these questions, they discovered more and more relationships. And these relationships got more and more complicated, to the point that they really stopped applying to land surveying altogether. According to the writer Proclus, it was Pythagoras of Samos, yes, the Pythagorean theorem Pythagoras, who was the first to assert geometry as a study in its own right, about the relationships between abstract geometric figures unconcerned with physical applications. And as geometry diverged from its original practical purpose, the goals of the people that studied it became more abstract as well. You see, back in Thales' day, it appears that getting the theorem was the goal. Now, Thales did demonstrate why all of his facts had to be true, but as the math historian Heath points out, he most likely did this by providing intuitive or empirical reasons why they should be true. But later Greek mathematicians would take this idea of justifying your claims to its fullest extent, beginning to insist that every geometric fact be proven true. And this is asking for something way more rigorous than just a demonstration. A proof is not an intuitive explanation demonstrating why something could be true. It's an undeniable chain of reasoning showing why a theorem has to be true, given some root geometric facts. And this was truly unique to the Greeks. No culture before them put nearly this much emphasis on justifying their knowledge. In fact, in nearly all the Egyptian and Babylonian math documents we found, they don't even explain how they get their theorems. But in Greek geometry, the theorem is just this tiny little line at the top of the page. The bulk of what they were recording is their ironclad explanation for why their theorem had to be true. And this seems like a daunting / impossible task, to take a complicated fact and prove it must be true. But the idea is one we've seen before. Just like how the Egyptians used simple tools to do complicated things, and Thales used simple measurements to know complicated things, the Greeks would use simple facts to prove complicated facts. And if you thought the Egyptian method for constructing right angles or Thales' method for finding the height of the pyramid was satisfying, then you will love Greek geometry proofs, because they're all insanely clever like this. For example, one very famous fact is that the angles inside of a triangle will always add to 180 degrees. Which for me is completely unintuitive. I mean, forget the 180 for a second. Just the idea that every single possible triangle is supposed to work in the same way is crazy to me. I mean, we could do some tests in particular situations, but how could we ever know this works for every possible triangle? And here's where the genius comes in. We're not going to start with this complicated, unintuitive fact. Instead, we're going to start with this simple, much more intuitive theorem called the alternate interior angles theorem. That just says if you have a pair of parallel lines and a third line intersects them, then this angle here and this angle here have to be equal. Which feels pretty intuitive, right? I mean, if you twist this line by a degree, then sure, the top angle has to change by a degree, but so does the bottom angle. So no matter what, these two angles will always be the same. Now with that intuitive fact in mind, let's go back to the triangle sum theorem. Consider literally any possible triangle you can think of. We'll color one of the angles red, one green, and one blue. Now no matter what triangle you're dealing with, go ahead and extend out the base of that triangle into a longer line. And then here's the clever part. Draw in a line parallel to the base that goes through the top of the triangle. That's clever because now that we have parallel lines, our simple parallel lines fact will apply. So by the alternate interior angles theorem, as these two lines are parallel and this line cuts through them, this angle and the red angle have to be equal. And again, as these two lines are parallel and this line cuts through them, the blue angle and this angle have to be equal. But then looking at the top, we see we have the red angle, the green angle, and the blue angle, the three angles of the triangle, when put together go halfway around a full rotation. So half of 360, which is 180 degrees. Which means the theorem is true. And I think this is so satisfying. Just by applying this simple fact twice, we get all three angles in a row right where they need to be, and the theorem just falls out. How good is that? So the point is, we just showed that if you take the simple parallel lines fact to be true, then the triangle sum theorem has to be true as well. Meaning we've just used a simple fact in a very clever way to prove a complicated fact. Now this theorem we just proved is what's known as a universal statement. That's one that asserts that everything in a certain category works in a certain way. But there are other types of statements out there. In particular, the type of statement that Euclid especially was obsessed with proving is existential statements. These are statements that assert certain geometric shapes even exist to begin with, which is not at all obvious. Not everything you could imagine existing actually does exist. For example, I could imagine a 2, 3, 6 triangle in my head. It looks something like this, with sides labeled 2, 3, and 6. But in reality, if these sides were actually those lengths, the 2 and the 3 side would not be long enough to ever meet up with each other. And no matter how you tried to finagle these sides, this triangle just would not work. This is a shape that does not exist. But the issue is this kind of brings the whole game into question. I mean, if you think about it, how do we know any shapes exist? How do we know an equilateral triangle exists? How do we know squares exist? How do we know in that last proof that parallel line we added actually exists? The Greeks' answer is that we don't. Or at least not at first. We have to prove they exist. And to do this, we can employ the same idea we use for universal statements. Use the fact that simple shapes exist to prove that more complicated shapes must exist as well. So for example, let's look at equilateral triangles, which to be clear are just triangles where every side has the same length. Again, I can't imagine them existing, but how can we be so sure this won't be like the 2, 3, 6 triangle example, where for some reason in reality, the sides of the shape just won't quite connect or just something goes wrong? And the answer is, I kinda don't. Triangles are a bit complicated. So instead, let's start with some simpler shapes that I have way more confidence in. For one, I feel pretty confident that at any point there can exist a circle of any radius. I don't think that's too complicated. And I also believe that between any 2 points there will exist a straight line. I hope you're with me there too. But if you believe in just these 2 shapes existing, just circles and lines, then you can prove that equilateral triangles must exist as well. Here's the idea. Start with any line of any length. We're going to show there must exist an equilateral triangle with all sides having that length. First, because we believe we can make a circle at any point with any radius, then we believe there must exist a circle centered at the left end of this line with a radius equal to the length of the line. This has to exist. And similarly, there would have to exist a circle centered at the right end of the original line with the same radius. Now these circles will intersect at 2 points, but let's focus on just the top one. As we believe there exists a straight line between any 2 points, then there must exist a straight line between the left end of the original line and this top point. And then by the same idea, there would also have to exist a straight line between the right end of the original line and this top point. And voila! We've just shown that this triangle here has to exist. But is it equilateral? Are all of these sides the same length? Well, let's remember that by definition, a circle's a shape where every point's an equal distance from the center. We call that equal distance the radius. So because the left side of our triangle and the base are both radii for the same left circle, they must have the same length. And similarly, because the right side of our triangle and the base are both radii for this same right circle, they must have the same length. Meaning all 3 sides of our triangle have the same length. This is an equilateral triangle. Equilateral triangles have to exist. And this is interesting because it turns out you don't have to take the existence of equilateral triangles for granted. As long as you believe that circles and lines exist, then equilateral triangles must exist as well. And we can do a very similar thing to show that squares have to exist too. But to do so, we're going to have to make one more assumption, that right angles exist. Which again, I don't think is that huge of an assumption. I don't think it's crazy to believe that given any line, there will exist another line that intersects it at a perfect right angle. Now the actual proof is pretty similar to before. Again, we're going to start with any line of any length. And then from there, we know this circle has to exist. And then because we believe right angles exist, we know this line right here has to exist too. And then this other circle has to exist, and this other line coming off at a right angle must exist as well. And then finally, between these 2 points, this last line must exist. And there you have it, a square. If circles, lines, and right angles exist, then squares must exist too. We don't have to take them for granted either. But do you see the connection here? The way the Greeks proved a shape exists is by showing you can build it out of circles, lines, and right angles. The idea being if they exist, then anything you build out of them must exist as well. But finding clever ways to build things out of circles, lines, and right angles is exactly what the ancient land surveyors did. Each of these proofs is just an abstract version of a clever land surveying technique, one you could use to construct that shape using just the circle tools, line tools, and right angle tools the surveyors/builders would have had. And this is most likely why the Greeks considered the circle, line, and right angle to be the fundamental shapes whose existence they took for granted, because they were still working in the tradition of the rope stretchers, where these were the easy shapes to make. So now that we know we can use simple facts being true to prove that complicated facts must be true, we've entered the exciting primordial stage of Greek mathematics, where with every new proof, mathematicians are adding to this massive disorganized web of facts, showing that if this fact over here is true, then these facts over here have to be true. And if these are true, then this fact is true. And if this fact and those are true, then these over here have to be true. It's a whole mess. But the dream of Greek mathematics would be to organize this tangled web of facts into a systematized sort of tree, where the bottom of the tree there'd be nothing but a very small number of simple, intuitive facts. And then every other geometric fact with increasing complexity would branch out from there. The idea being, if this tree actually existed, then you just have to believe the simple intuitive facts at the bottom of the tree to know the rest of geometry must be true as well. And potentially starting with Pythagoras, mathematician after mathematician organized their own versions of this tree, constantly growing the tree to accommodate new facts and rearranging the tree in a way so it could be more easily navigated. And as time went on, people chipped away at the bottom of this tree, trying to find the fewest, simplest possible facts at the root of all geometry. And in the process of this, mathematicians discovered that a lot of facts that feel very fundamental actually themselves are caused by even more fundamental facts. For example, the opposite angles theorem is actually just a consequence of the alternate interior angles theorem being true. And Thales' theorem you can show is true from the isosceles triangle theorem and the triangle sum theorem. And even something as fundamental as the existence of right angles, we don't necessarily have to assume. The mathematician and nobody showed that if you just assume circles and lines exist, then you can show that right angles will have to exist as well. You don't have to make an extra assumption. And nobody's proof of this one is especially fun because it involves a callback to Thales' theorem. The idea is, given any line and a point on this line where we'd like a right angle, we're going to construct a Thales theorem-like situation around this setup, aiming for the right angle to coincide with this point. Start by plopping a new point down literally anywhere in space not on this line. Then we know there has to be a circle centered at that new point going all the way to the point on the line. That circle will cross our line at 2 points, the point at which we'd like a right angle and a second point. Then we know there has to exist a line going through this second point and the center of the circle, which will be a diameter line, by the way, since it goes to the center. Then finally, there has to exist a line between this point, where the diameter intersects the other side of the circle, and the original point where we'd like a right angle to be. But look what we have here. We've created a triangle inscribed in a circle where one of the sides is the diameter line. Meaning, by Thales' theorem, the corner opposite this line must be a 90-degree angle, exactly at the point where we wanted a right angle the whole time. If circles and lines exist, then this right angle will have to exist as well. We don't have to take the existence of right angles for granted. We can show that it naturally arises from the existence of these more fundamental shapes. And notice, by the way, if you did all of these steps with the physical circle tool and line tool, what you'd have is yet another surveying trick for constructing perfect 90-degree angles. It all comes back to land surveying. And so, as the dust settled, the Greeks discovered that there were way fewer fundamental facts in this web than you would initially think. Almost all facts, even the really simple ones, are just side effects of these few fundamental facts being true. And the mathematician that took this further than anyone else was none other than Euclid of Alexandria, who, in his book The Elements, went through and meticulously did every single clever proof he had to do to show that if just 5 simple facts are true, then everything else in Greek geometry has to be true. Yes, in Euclid's organization of geometry, there are just 5 fundamental facts at the bottom of it all. They are, in the order Euclid presented them: 1. Between any 2 points there exists a line segment. 2. Any line segment can be indefinitely extended in either direction. 3. At any point there can exist a circle of any radius. 4. All right angles are equal. And 5. The alternate interior angles theorem. More or less this means, if you believe lines and circles exist, plus that parallel fact, then you know that every other Greek geometry fact has to be true. And I'm not just talking about the simple ones. All of the 173 facts that Euclid proved in books 1 through 6 must be true. We're talking the Pythagorean theorem. We're talking squaring the lune. We're talking the existence of a regular heptagon. All of these have to be true just because lines and circles exist. And this is why the Greeks were so obsessed with the straight edge and the compass. Because even though they were just 2 simple tools that could only make 2 simple shapes, just lines and circles, those are all that you need to do all of this. All right, that is the story of where Greek geometry came from, but it's not the story of where it went after Euclid. As we already discussed, after it was lost and then refound, Euclid's Elements became the standard geometry textbook in the West taught to every learned person. And to anyone who studied the elements, what Euclid really proved is how unreasonably effective reasoning can be. I mean, literally from just those 5 facts and no other inputs, no other observations, no other data points, Euclid just figured out through sheer logic those other 173 geometric facts have to be true. It makes you wonder, if you can do this with geometry, what's stopping you from doing it with any other field? And it's my opinion that thanks to the influence of Euclid's Elements, that's exactly what people started to do. I mean, take physics for example. In the 1600s with people like Descartes and Newton, physics became way less about categorizing and way more about trying to understand a few basic principles from which everything else could be explained. For example, Newton's 3 laws of motion plus his law of gravitation could be thought of as fundamental, irreducible facts from which we could figure out a lot of classical physics. And famously, during the Enlightenment, people started applying these ideas of logic and reasoning to government and politics. Some even say that Thomas Jefferson was directly inspired by the elements when writing the Declaration of Independence. After all, at the top, he starts with, "We hold these truths to be self-evident," introducing his fundamental, irreducible facts. Then he spends the rest of the document using those simple self-evident facts to show why the United States has to be independent. And so now that you're a part of an exclusive club of people that have learned from Euclid, what I hope you'll take away from this conversation is the power of simple tools and simple information. Because I think these days everyone thinks they're going to solve their problems with the next biggest, fastest, strongest thing that has more data and more compute. But what the rope stretchers and Thales and the Greek geometers and especially Euclid would tell you is that you can do a lot with just simple tools if you're only clever enough. Okay, so thank you to everyone who actually made it to the end. This was the longest video that we've made by far. And basically when I was researching this video, I kept finding more and more things, but I didn't want to take anything out because I think this was an important story to tell. But if you like stories like this, please consider liking and subscribing because we'd love to grow this channel and make more videos and reach more people with cool, fun math stories. And every little bit helps. Have a good day, everybody.